Remember, I mean, labs you need at least a 70% average to pass the class, regardless of how you do on the finals, exams. You still need to pass. Basically, need to pass the labs in order to pass the class. So just keep that in mind. So don't blow it off or take it too lightly. How many quizzes have you had in recitation so far? Oh, so for the second half, right. I see. Okay. Cool. All right, so let's get started. So last time we looked at oscillating waves, oscillating charges, and how it creates oscillating electromagnetic fields. And before I forget, we ended last time, of course, before we did the Pink Floyd tribute, we discussed fiber optics and critical angles and critical angle and so on, right? So this more or less represents a piece of fiber optic for all intents and purposes. And this is just a laser pointer. So it stands to reason that if I were to shine this laser through this at a certain angle, I mean, or above a certain angle, then it's going to be totally internally reflected and I'll get light out of there. So let's take a look at this. All right. So I shine it through here. Yeah, I don't know either. It's going through there, so you need to find the critical angle. Well, I mean, this is a fat fiber, so it's the whole laser is going to get dispersed along this width. So if you guys look at the tip of this, once I shine, you guys can see the light coming out through there. Right? So if it stands to reason that the fiber was really thin to more or less match the width of this laser, then you can see actually a beam going out there. So, but because it's a thicker piece of plastic or plexiglass, whatever it is, you won't be able to see a nice defined dot coming out. But you guys can see that the light is totally internally reflected here. And if you look closely enough, you can see the points of reflection here. I got it coming over there, reflects down there, comes back over there. And I can change that number by changing the angle. Right? So total internal reflection. All right, so before that, we looked at oscillating charges. So accelerating charges, if you accelerate along a plane, it creates electromagnetic waves, and those are all going to be along one plane. So they're polarized. Now, it's easy to determine the direction if you know the direction of oscillation of the charge. So if my charge is to oscillate along this axis, and I have another axis over here, then if I let my electric field over here, the direction of this is going to be something like that out of the plane. So this is the r vector I'm looking at. This is my electric field, and that's a certain point I'm looking at. We know that at this point, P, we know that the electric field is always perpendicular to my r vector. And also the direction of propagation is always perpendicular. And it's the acceleration, the r, and the electric field are all in one plane. And we also saw that in a situation like this, I have a point charge Q, and my electric field is proportional to Q A over R sine of the angle between them. So then this being my angle. And of course, I'm oscillating this at a certain frequency omega, which means that the electric field in turn is also going to oscillate at the same frequency omega. From the electric field, we were able to extrapolate the Poynting vector, or at least the magnitude of it, because it's on the order of the electric field squared. So it's something to the effect of Q squared A squared over R squared and sine squared theta. And this R squared we need because of the conservation of energy due to the surface area of the plane we're looking at. So we need that R squared over there. And we looked at this experiment, and I kind of rushed through this and also realized that this thing woke you guys up, so I figured I'd do it again. So this, as I mentioned last time, was a radio transmitter and a microwave. They're approximately around the gigahertz range. So this is approximately, the frequency is about 10 gigahertz, which gives me a wavelength of around 3 centimeters. And as I said, this is essentially radar or microwave. Now, what this looks like here is, if I take a certain three-dimensional plane and I have accelerating charge along this direction, I'm accelerating this charge along this direction, and then it produces an E field about over here, right? And this is my R vector. So again, the acceleration, the R and the E are all in the same plane, as you can see there. And what we did with this is we had this frequency, the gigahertz or 10 gigahertz frequency, and we modulated the amplitude with the audio signal. And we discussed this before when we discussed radios, essentially how radios work. And we did some amplitude modulation for this, and we got a 1 kilohertz annoying tone that woke you guys up. So when I turned it on, we were able to hear that annoying tone. And when I went through with these little slits, we were able to see that, okay, it is in fact polarized. So let's listen to this one once more. So by the way, yesterday's lecture was originally up. Monday's lecture was originally up, but then YouTube was giving me grief for copyright infringement for having the Pink Floyd song in there. So I need to go back and edit that out. And but for the people that appreciated that, the actual full version I'll put up on my website in its high definition glory. So what's that? All right, so we're all able to hear this annoying tone, right? And these two are in plane. If I take this, so they actually didn't set this up properly, as it turns out. So this is the perpendicular, so you can barely hear it. Let me turn the volume down. So you guys can see that this is actually the opposite. So let me fix this. All right. There we go. I take this in, nothing happens, basically almost goes away, right? So we know that this is polarized along a certain direction. So if I have it along this way, if I have it vertical, so I have where's my marker? So if I have something like this, and these bars are vertical, this thing kills it. It basically absorbs, this thing absorbs all the waves. When it's horizontal, it doesn't. Basically, lets everything go through because it's in plane with the transmitter. So you see a nice, or not see, but hear a nice annoying tone. But when the gratings are vertical, then it's perpendicular to whatever plane it's transmitting in, and then it just kills the sound. Another thing is radar. Who else uses radar besides military? You do? Airplanes use it. Yeah. So all those use radar. I mean, for them, it's. I mean, the waves are actually polarized. So my first thought was, okay, I got this big fat speeding ticket a few years ago, and the police obviously use radar guns, right? So I figured, okay, now if I were to somehow come up with a paint on my motorcycle that basically would absorb all the frequency, or have one of these like a cage around me that would absorb the police frequency, I wouldn't get any more tickets. But I know the police radars are actually vertically polarized, but then they can just turn their guns around and they can clock me. And I figured if I were to try to block the radar, they'd piss them off more, and then they'll just come after me. It was an interesting topic. I know this was another conversation I had with my professor in undergrad, and he was telling me about his friend who worked for a defense company out near the coast, and he came up with this special carbon compound paint that he coated his entire Porsche with. And what this does is, how does the radar work? You have the radar gun that the police uses, hits your car, reflects off, and then the device measures the Doppler shift, and then they say, okay, you're going 100 miles an hour. So if it absorbed everything and didn't reflect any of that waves back, the police wouldn't really know what speed you were going on. Of course, it wouldn't work if they're right behind you, clocking you. But so he said his friend was going up and down the Pacific Coast Highway at 100 miles an hour every day to work, and never got a speeding ticket. So I thought about using that on my motorcycle, but then I have to code everything, including myself, with that, and yeah, so it didn't quite pan out. So I just slowed down. All right, so back to the light stuff that we discussed at the end yesterday. Now we discussed briefly what white light was, and its significance, colors, and all that. Now, if you were to ask a physicist, when do you see certain colors? I mean, given how crazy physicists are, you'd get some obscure response, and they'd probably tell you something along the lines of, well, the chance that he or she would give you a standard answer would be quite small because they're a little crazy. So what they'll probably say is, well, it depends on the wavelength and that you see in the air. And if you tell me the wavelength, then I can tell you what kind of color you'll see. And we know that it follows color has a certain spectrum, right? Certain frequency will give you a certain light. Let me pull that up for you guys. Right, so we have here, as you guys can see, so the units here are in terms of angstrom. Angstrom is 10 to the negative 10th meter. So red is relatively longer wavelength, and it goes down to violet, which is quite shorter. So anything before this red wavelength is infrared, and so on. Anything beyond this violet is ultraviolet and stuff you can't see. So basically, the other ends of the spectrum we can't really see. And what I showed you here between red and violet is what we consider to be visible light. So that's what we can actually see. And over here you have longer wavelength, as you can see, and it goes down to shorter wavelength. And we also know that energy is inversely proportional to wavelength. Right? So what's energy? What's that? Well, before MC squared. I mean, I'm sure you guys have had chemistry classes, right? Yes. So it's Planck's constant h over the wavelength lambda. Now, so basically the story here is, now this is obviously some constant, so E is basically inversely proportional to the wavelength, which is to say that it is equal or proportional to the frequency. So the shorter the wavelength I have, the higher the frequency, which means higher the energy, and vice versa. The shorter the higher the wavelength, larger the wavelength, shorter the frequency. Does it make sense? Yeah, higher the wavelength, shorter the frequency, and shorter the energy. So white is a mixture of all these colors, and it's actually not quite so simple because quite a few people have worked on it to sort of arrive at some similar conclusions. The issue of colors has been worked out in details in the 17th, 18th, 19th centuries. And at the time it was discovered that there's such a thing as primary colors, and it wasn't just the artists that came up with it, it was also proper scientists, Maxwell and Helmholtz, also arrived at that conclusion, and they did a considerable amount of work on this. And they discovered that if you had the primary colors, and essentially the three primary colors we see are green, violet, or they said were green, violet, and red. And when we mix paint, you see yellow, blue, and red. Blue and red? No, yeah. So they said when you look at something, you have that. And the idea being that a mixture of these three colors can yield the whole spectrum. And they came up with a triangle of a type. And they said up there was green. We have some markers. So they said up here was green, and down here was red, and over here is violet. And essentially a mixture of these would give you the color you need. So if I were to make a color at point P here, right? So what I would do is, okay, I would need a certain amount of red. Where's my black? So I would need a certain amount of red. I would need a certain amount of violet. I would need a certain amount of green. So the amount of green I need is dictated by the length here. And the amount of red I need is dictated by this length here, and the amount of violet I need is about that much. And the combination of those three gives me the color at that point P. If I wanted yellow, for instance, it would be somewhere along this, which means that I need a certain amount of green, a certain amount of red, and no violet, and that would give me yellow. And then if I want orange, I can slide further down, so I add more red but less green, and that would give me red, and not red, orange, and so on. And essentially a mixture of all this, if I were to look in the middle, a combination of all these colors, our brains will trick us into thinking that we're actually seeing white light. So this issue was studied for quite a bit, and this is also a similar principle behind the TVs that you may have had at some point. Does anyone still remember here CRT TVs? Yeah, all right. So I'm not as old as I think. What's that? Well, I'm not as old as you think. I'm not that much older, at least. But you guys are all born after the 90s, or born in the 90s. So yeah, I'm not that much older. Actually, you're older than me. So the principle behind CRTs is similar. You have electron guns, right? That shoot, not shoot, but basically uh, give out different well, beams of electrons. And then what you have is three different chemicals on the screen itself. And what those chemicals are, they're in the shapes of little dots, as we would now refer to as pixels. So you have pixels essentially on the screen, and if the electrons hit one of these dots, it becomes violet. If it hits one of the other dots, it becomes red. If it hits one of the other dots, it becomes green. And so you had the mixture of these three, violet, green, and red, and that combination of all three gave you white. So different intensities hitting those different dots yielded different colors. And you had those three guns; they're shooting dots all throughout, and you got essentially your big color TVs. And back in the day, I think the maximum resolution was obviously around 480. So the amount of pixels were still more or less the same, no matter what the size was. But the size of the pixels essentially changed. But now that those things are changing, now we have fancy LCDs, LEDs, organic LEDs, and also you have the resolution also changing. You have different densities. You have the standard TVs are 1080p now, and the new ones that are coming out are 4 times that. You have the 4K TVs. So a lot of fun stuff in terms of color. I know Sharp came out with a new TV recently that had 4 primary colors according to them. And what's that? You're adding essentially, if I have lasers essentially shoot out that particular color. So if I have this particular frequency of pure green, which you would consider, and red and violet, you would add. It's basically a matter of ratio. So if I had those 3 beams, I would pick the ratio that I would need, and I would of the ratio of the intensities of what I would need, and it would give me that particular color. So it's a matter of ratios there. I mean, like I said, this is a pretty archaic one, so it's just to provide context. And on those old CRT TVs, you had to, if sometimes the color went out of alignment, is because there's the beam guns, they were shooting at some odd direction. So as soon as you adjust the beams, the guns, then everything worked more or less properly. So starting in the 19th century, that's when the 3-color theory became popular, and it of course had its problems. There's a particular guy named Benham. This was an interesting fellow. He came up with Polaroid, the instant Polaroid photography. Came up with polarizers, and he did a lot of stuff, a lot of pioneering work in the field of color and photography and light and all that stuff. So he had an interesting experiment wherein he had a camera, black and white camera, and he put a red filter. Basically, if it's like looking through red glasses, right? So just put a red filter in front of it and shot a photo. Well, it's a black and white camera, so the end result you'll still see black and white photo, right? He took that filter off and took a picture again, same thing. Black and white photo, you may see more of the other shades of gray, if you will, that's been blocked out, and you have the other slide. Now if you superimpose both of these and put a red filter on top of that, you'll see a lot of red, but you'll also start to see other colors. You'll see some green, some blue. So it just went to show that it's not just so cut and dry black and white here. The color, the actual, the theory of color is a bit more complicated than it seems. So again, it evolved from that, and I guess the primary theory that holds now is you have RGB, right? Red, green, and blue. Those are the 3 primary colors. And when you're printing, usually use CMYK, different set, but yeah, so CMYK use that for that. So for printing, it's different, but as far as you can see and all that, it's RGB is considered to be the standard. So I mean, until someone else comes along, maybe one of you will go along and change what we perceive about color. Again, color is just what you perceive it to be. So its color is in the eye of the beholder. So we'll leave it at that. So now let's revisit polarization, which is, in my opinion, a more interesting topic that hopefully won't put you to sleep. So we discussed that, and I mentioned that that was electromagnetic waves that were polarized at a certain, well, in a certain direction. And we saw that if once I flipped this over, I got a certain direction of polarization as opposed to if it was going the other way. And we also demonstrated it with this. If depending on the angle I had it in, I got almost complete silence, or I got the annoying 1 kilohertz tone that was being produced. I think maybe next time I'll try to modulate one of these with Pink Floyd. Although then if I record it again, then YouTube will catch me again for copyright infringement. But now let's focus exclusively on polarization of light, which is obviously at much higher frequencies than microwave or radar. And light from our light bulbs that you see, and even from these, it's not polarized. So how does it work? You have, if you think of light as individual photons, and basically, those light photons, they'll have, each photon will have, light going along a certain plane, and they're all, each one of those photons will have a well-defined direction of light going through. But if you add a bunch of those photons, there's no particularly preferred direction, at least coming from the light bulb, coming from the sun. So we say that that is polarized. So if I were to think about it, what I would have is, if this were my photon, I could have the light traveling in that direction. Another photon will give me light in that direction. Another one will give me light in this direction. Another one will be in this direction, and so on. I can just keep going on. So there's no particular preferred direction overall as an aggregate of this. So if a beam of whatever that you're able to see there, if this beam of light is coming straight out of the board, it's going to be, if I take one photon, then it's going to be linearly polarized. If I have this particular thing, one photon is hitting you guys, then that beam is going to be linearly polarized. It's in a straight direction. Once I add everything up, then it's not polarized. You have light going in all directions. But if I just take one beam coming from the board to you, it's going to be along one plane, one direction. And if I add another one, then it will arrive along there. So if I were to look at polarizing filters, now I can see two separate ones. Obviously, you have a bunch of light coming from here, but idealized case. So again, what you have here is no particularly preferred direction for the light that's coming towards you from light bulbs, from other sources that are not exactly polarized. And we call that unpolarized light. So this is, in all directions, unpolarized. And again, this fellow Edwin Land, Benham. That was Benham. Was that Benham? No. So that was supposed to be Land. Benham was another guy. So this guy that I mentioned, it's actually supposed to be Land. Land was the one that came up with Polaroid and all that. Benham was another guy. Benham was the guy who came up with Benham top, which basically had some sort of a wheel. Like a certain black thing here, like different lines over here, and you rotate that. It's basically, this whole thing is black and white, either black or white. And when you rotate that wheel at a certain frequency, you can see colors. So it's just his way of showing that it's all an illusion and so on. And that's because of a change in, like, a frequency lag. That's why you're able to see colors, but that's insignificant. But what I meant for the whole polarization thing was Edwin Land. So Edwin Land, again, during the 1940s, when he was at Polaroid, he came up with the material that was able to turn unpolarized light into linearly polarized light. And this, in addition to the colored stuff I mentioned, that the photograph things, the two photographs, that made him quite famous. So Edwin Land's sheets. I requested something else here, then they didn't bring it. Well, these guys had demonstrations with polarized sheets, but I'll get them on Friday. All right, so you had basically light, all the light coming through. It would just give you light in one vertically polarized direction. So if I were to have one photon again going, now this is my straight axis, I have a photon going in some direction, this is my E naught at a certain angle. Then when I pass it through the, when I pass it through the polarizing filter, I would get that particular photon would be polarized. So if this was at some angle theta here, which means that this is also at the same angle theta, then the component that I would get back now that's coming along this way is going to be E naught cosine of theta, right? And that's essentially what I got when I passed that photon light through the polarization filter. So when I pass that through any light through a polarization filter, the question is, will it change the intensity? And the answer is yes, it actually absolutely will change the intensity, because the pointing vector, remember, is proportional to E squared, right? In this case, E naught squared is proportional to the amplitude. So in this case, once I pass it through a polarization filter, it will be proportional to E naught squared sine squared theta. Sorry, not sine, cosine squared. And if I were to take the average of all the photons over everything, then this cosine squared theta will essentially boil down to 1 over 2. So once the light goes through the mean value, so if I have an aggregate amount of light, unpolarized light going through a polarizer, then the intensity on the other side would be half. So this would basically mean that the polarized light is going to be half the intensity of the light going in. So that's your first pass. And so for instance, we usually define I naught to be the initial intensity. So if I have I naught intensity going in the polarizer, right, and what I would end up getting is I naught over 2 on the other side. And this is if it's 100% polarized. Again, so this 1/2 is a result of the average of 1/2 of cosine squared theta. Now, 100% polar. So these filters, you have different separate types of polarization filters, and a particular filter that's called HN50. This basically means that it's 100% polarized. And you may see this referred to in some literature, but this kind of filter doesn't actually exist. So this essentially means that the light that's coming out is 50% of the intensity, so they say 50. So most of the like the really good polarization filters you'll see are pushing that limit. So it's something like HN40, HN45, but they'll never achieve that 50. So now let's take some unpolarized light. Right, so let's say I have light coming in this way, right, at some intensity I naught. I have a vertical polarizer here, right? So the light would go through that, and the light that I would get on the other side is going to be 1/2 I naught at this direction. The direction is going to be vertically polarized like it is here, and that's going to be my intensity outside. If I put another polarizing filter over here after that, and it's at some angle theta, right? So this is again a vertical polarizer, at least according to its plane, it's a vertical polarizer. So the light that's coming out through here would stand to reason that it's 1/2 I naught cosine squared theta. Right? Now this won't simply be another 1/2 because I only have light in one direction. So I take that and I basically now have to look at the cosine of the angle, the cosine component of it, to see how much light is actually coming out of there. Does it make sense? You guys look a bit puzzled. We're good? So far I have unpolarized light coming in, I naught intensity. I pass it through a first polarization filter, and what I get in after that is half the intensity, so 1/2 I naught. It's polarized along the vertical. I have another vertical polarizing filter, but I tilt the angle a little bit. So if it's at 0 degrees, right? So all the light that's vertical will pass through the vertical filter, no problem. There's going to be no intensity change. So cosine of 0 is going to give me 1, which means that it's simply going to be 1/2 I naught. So at some angle, I'd get some percentage of that intensity passing through. Now if this angle, if theta were equal to 90 degrees or pi halves, what would I get? 0. I wouldn't get anything. So those of you who have polarized sunglasses, I'm sure some of you in here have them. There we go. Now you can take out your cell phone, look at the cell phone screen, and look with your glasses, and if you look at a certain angle, you won't see anything. Because the LCD screens that we see, are laptops, desktops, or phones, tablets, whatever you have, they're all polarized in a certain direction. So if you put them through a polarizing filter, which the sunglasses you have are a type of polarizing filter, if you change the angle to a certain angle, you would get complete darkness. You wouldn't see anything. So that basically, according to that, you have a certain plane at which the screen is outputting the light, and you have a certain plane of polarization for the glasses. And if those two are 90 degrees perpendicular to each other, then none of the light will pass through, because what you have here coming out is you have light that's all vertically polarized. And if I have a polarizing filter that's horizontal, it would not let any of this vertical light through. So if it's at some angle, it would let some component of that filter, of this light through, and you'd get some fraction of that intensity. So this law, whereby the intensity is reduced by a factor of cosine squared theta, this is called Moll's law. L-U-S, Moll's law. So for example, if this theta were 30 degrees or pi 6, right? The intensity after the second polarizing filter would be 1/2 I naught cosine squared theta, wherein theta is pi halves. So I get 1/2 I naught cosine squared of pi 6. So if I look at my right triangle here, this is pi 6. So this is going to be 1, 2, square root of 3. So cosine is adjacent over hypotenuse, so it's root 3 over 2. So I would get 1/2 I naught root 3 over 2. Right, this is going to be squared. So this is going to be 3 over 3/4 times 1/2. So this is going to give me I naught times 3/8. Right, so it's 3/8 the original intensity going through. And you pass it through another set of filter at some other angle, it'd go down even further. So you can keep passing these through filters. Now a problem with this is light, as I mentioned before over there, contains energy. Right? Now each frequency has a certain energy, so it would imply that if the energy were to go down, then the frequency were to go down, and so on, so the wavelength would change. So blue light, we know, is at a higher frequency, at a shorter wavelength than red light, so it's higher energy. So after I pass blue light through a polarizer, the intensity would go down, which means that the energy it has will also go down. So in principle, you would think the frequency also should go down, right? So the wavelength should go up in principle, but it doesn't. So if you pass light through a polarizer, the energy will go down, but the actual wavelength will not. And you sort of have to take it at face value here that it won't, because in order to explain that, you need quantum mechanics. And interestingly, once you use quantum mechanics, you arrive at the same conclusion, same results that we did over here, and it will also tell you the same thing, that it doesn't change the frequency. So for those of you taking quantum mechanics, you'll get the chance to see and experience that in the future. Now, this is one way of creating polarized light. We looked at polarizing filters. Another way of creating 100% polarized light is that it's accomplished by reflecting unpolarized light off certain dielectrics, such as glass, water, and so on. And then you'd get also 100% polarized light. And this doesn't actually follow from Snell's law. Snell's law basically tells you you pass light at a certain surface, water, glass, whatever dielectric. Part of it would get reflected, part of it would get refracted, and no change in energy or polarization there. So Snell didn't know about this, but this was discovered after. Because Snell was, around 200 years before Maxwell? So Snell didn't know anything about this stuff. But we also know Maxwell's equations allow you to properly deal with this reflection and refraction, including polarization, if you know how to work through the trig and the agony of all the substitutions. So the derivation for that, to look at how reflected or reflected light is actually polarized, the derivation of that is beyond the scope of this class. And for those physics majors moving on, I would recommend looking at a book by the guy named Wangsness. So this is actually a pretty good book, and it may even be like a recommended text along with your upper division E&M class. So that book has a proper derivation for all this stuff. So now, looking at a more layman way of looking at it, what we have here is, I'm saying this is some media, I have some unpolarized light coming in. Right? So this is coming at some angle theta 1. It stands to reason that it would bounce off at some angle theta 1, and it would get refracted here, and this would be theta 2. Right? And we know that this is some media N2 or N1, this is N2. Now if you want to use Maxwell's equations at the surface, you have to decompose the light, the incoming light at least, into the electric field vector in 2 dimensions. So at this point here, we'll call this, we'll use a different marker. So at this particular point, if I have some photon, I have an E field coming out over here. And I also have an E field that's perpendicular to this. So this is my, I'll call this my perpendicular incident. And then I also have an E field that's along in this plane. And we'll call that incident that's parallel. Same thing over here. I would have some E field coming out, some of it in this direction. Same thing over here. I would have something coming out and something in along this direction. So this is my reflected, and this is my refracted. So this is again, this point is my perpendicular one, this is my parallel one, perpendicular, parallel. So this is perpendicular to the plane I'm looking at, this is parallel to the plane we're looking at. So notice both the components are perpendicular to the direction of propagation. So both these two components, these two, they're all perpendicular to the direction of propagation. So from the incident plane, we can, the incident light is not polarized, so there's no preferred direction for the electric field. Now, we know that the because it has no preferred direction, the electric field that is coming out and the electric field that is parallel over here, the intensities are both the same. Now, what Maxwell's equations can do is it can relate this to that. So it can relate E perpendicular in the incidence to the E parallel in the reflected. Right? And you can do E perpendicular in the incidence to, wait, I'm sorry. Yeah, to E, sorry, parallel. E parallel in the incidence to E parallel in the refracted. So you have two equations there. You can also do E perpendicular in the incidence to E perpendicular in the reflected, and so on. So basically it's a lot of work, and you essentially get 4 equations. And you will see that the one that's perpendicular to the plane, the one that's parallel to the plane, their intensities are the same. And if you apply the equations, you'll see that it's no longer the case for the case where you have in the reflected part. So E for the reflected is no longer equal to, at least intensity wise, it's no longer equal to this. So originally these are equal, but now it's no longer equal. So this implies that the reflected and the refracted light has become polarized now, because the intensities are not the same, the directions are not the same. So let's look at one of the equations that this thing provides. So what I have here is that the E naught parallel of the reflected is equal to the E naught parallel of the incident. Right? That's what we're looking at. So from this, I can say, or this is equal to that times n1 cosine of theta 2 minus n2 cosine of theta 1 over n1 cosine of theta 2 plus n2 cosine of theta 1. And using Snell's law, again, this is simply Snell's law. Using Snell's law, I can simplify this too. Negative E naught parallel incident times the tangent of theta 1 minus theta 2 over tangent of theta 1 plus theta 2. I don't remember this. I don't expect you guys to remember this or know this. I have to look it up every time I deal with this. Now, if you're interested in the intensity, or no, you're looking at the Poynting vector, then remember it's squared of this term. So it's squared of the strength of that. Now, something that's interesting to look at is if I look at the angles theta 1, theta 2, when I look at theta 1 plus theta 2 is equal to pi halves, then the denominator here would go to infinity. Right? So when that goes to infinity, the reflected, the parallel reflected light is effectively 0, because the denominator goes to infinity, then this goes to 0. So basically the parallel contribution from this, from the reflection, is completely gone. That's if this is the case. Now Snell's law says we have sine of theta 1 over sine of theta 2 equals to n2 over n1. right? Now, if this is the case, then over here, sine of theta 2 is equal to the cosine of theta 1, right? Cofunction identities. So if this is the case, I can take sine theta 2, substitute this in, and what I end up getting for this now is I get sine of theta 1 over cosine of theta 1. This equals to tangent of theta 1. So so what I have over there is sine of theta 1 over sine of theta 2 is equal to n2 over n1, which is equal to tangent of theta 1. Now, I've met my condition for getting 100% polarized light because of this angle theta 1. And this angle theta 1 is a special angle, and we have a certain name for it because of some guy that did work on it. It's called Brewster angle. So if you have light coming in a certain angle and it reflects off at that angle, that particular angle, which is approximately, well, I'll derive it, but it's that angle is called Brewster's angle. So at that angle you get 100% polarization, and anything deviating from that angle you still get polarization, but it's not at its maximum level. So if I'm going from air to glass, right, and for the index of refraction for glass is approximately 1.5, as we discussed earlier. So plugging this in, my Brewster's angle here is going to be around 56 degrees. If I invert this and I go from glass to air, then my Brewster's angle is going to be 34 degrees. Right? Therefore, it's smaller. Again, as I mentioned, the derivation for this is in Langsness, and if you guys are interested, it's on page 405. I looked it up yesterday. So this is quite a remarkable result, that you got polarization from essentially Maxwell's equations. Although we didn't look at all the math, I'm sure you guys would be even more asleep than you guys are right now if we went through the math. So I'll spare you guys the details on that. It's not particularly within the realm of this class anyways. Now again, this polarization stuff we saw, or at least I told you guys, it applies to glass. So if you take your polarized sunglasses, or if you have some sort of polarizing filter on your cameras or whatever, if you change the angle about, you can see light reflect at a certain angle. You can see light, no light reflecting. You'll see completely through that glass at a certain angle. This doesn't apply to conductors, to metal, because the light is different on the surface of conductors than it is on the surface of dielectrics. So Maxwell's equation can be applied to the dielectrics also, so to the conductors also, but you get a completely different result. And you can never really expect to get linearly polarized light bouncing off metal. So if you see, certain cars have like metal, like chrome side view mirrors and stuff. So if you see, light reflecting off that, even with the polarizing sunglasses, and if you tilt your head around to change the angle, you won't see that reflected light disappear. So that's because of the way the surface is structured. So we looked at so far 2 ways of polarizing. Let's take a quick 5-minute break, and then we'll regroup and we'll go through the other method of polarizing. All right, let's get started again. So we looked at two methods of polarization so far. We looked at having polarizing filters linearly, or later on we'll go to different types of polarization. And the next one we looked at is reflection of surfaces, of dielectrics in particular, that also produces polarized light. Now, the third method to get 100% polarized light is scattering. Well, some of you have puzzled looks on that, so we'll get into that. So scattering is actually, the exact physics behind it is a bit complicated. And when we scatter, to get polarized light, it has to be of really, really small, tiny particles, something along the orders of 1/10 of a micron, so 0.1 micrometer. So that's about the range of particles that we can look at. And it just so happens that dust particles fall under that category. So again, as I said, this is complicated, so we won't get into too much math. I'll more or less explain the theory behind it. So if I have light coming in along this plane, I have a dust particle it hits, and it would scatter off in a different direction. And at this point, the scattering angle here is 90 degrees. And this, when it's 90 degrees, when it's perpendicular, this would provide 100% polarization. And the particular type of scattering we're looking at, there are different types of scatterings. The one we're looking at is Rayleigh scattering. So if I have a light incident at some plane, and I have a bunch of dust particles, what will I have? Basically from this, I have light coming in this way. So I have a certain electric field in that direction. So I would go through, hit this, and I would get some sort of electric field oscillating in this direction. So light has a certain frequency, omega, and it would get to that dust particles and oscillate at some frequency as well. Now, because it's oscillating, it would have a certain direction, and that direction, it would have a certain acceleration, and that acceleration can be defined by, we know acceleration is force times ma, or force over mass. So from this, we know the force over there is the charge times the electric field over the mass, and the mass for that is the type of particle that hits it. Now, obviously, we would have protons, neutrons, and so on, but the electrons would have a much higher acceleration here than protons would, because the mass of electrons is far less than the mass of protons. So because we're dividing it by mass, because the mass of electrons is lower, we'd get a much higher acceleration, in fact. So electrons, in fact, would do most of the job here when it comes to scattering. So I have electric field here, and it scatters or bounces through, and if I'm looking at some point over here at some distance r, their scattered light would be something like this. It would be perpendicular to that distance I'm looking at, and my electric field would be oscillating in that direction. And remember, we've discussed this before, the electric field is always perpendicular to r there. And again, the acceleration, the r vector, and the electric field are all in the same plane. So when this comes in, hits the particle of dust, the incident photon is completely destroyed, but it is absorbed basically by the dust. And then the electron that scatters off, that thing radiates another photon. So that's where you can see a different direction of light. So basically, it re-radiates a photon at exactly the same frequency, but because it goes off in a different direction, the thing would have a certain polarization. So the photon comes in and takes a different direction from there, and that's what we call scattering, because the electron comes in, or photon comes in, gets absorbed, electron scatters away at some direction, and it's usually polarized, and the electron itself would re-radiate a different photon, but at the same frequency, so you wouldn't see a shift in color or anything. Now, when it's accelerating in this direction, it basically becomes a probability as to which direction the photon would go in, or the electron would get scattered in. So if it's accelerating in this direction, the probability that the electron will get scattered in the direction that the electric field is oscillating in is 0. Right? So in this direction, the probability is 0. The highest probability would be when it's perpendicular to the direction of acceleration. So if I have, this is my acceleration along some plane. So if this is my, I'm accelerating along this direction, the plane around that's going around this pen, that's where I would have the maximum probability, the highest probability, going along this way. So it's highest probability when it's perpendicular to A, to the acceleration at which it's oscillating at. And the light that comes off and scatters, as I mentioned, at 90 degrees, it produces 100% polarized light. Now, does everyone here know about the physics festival we have during the spring? You guys heard about it? Have most of the people here been to that? No? All right. Well, there's a particular demo there that I requested, but they weren't able to get it, so I'll just explain away at the demo. So, as I mentioned, the incident photon is completely destroyed over there. So let's take a beam of light. Beam of light coming about from down here. So I've got a beam of light. It's not polarized, so it's in all sorts of direction, no particularly preferred direction here. And basically individual photons that over there would have individual directions of polarization. So as an aggregate, it would come off as unpolarized. But individual photons themselves will have some sort of a direction. So I take this beam of light, I shine it at some dust particles up here. So what I would get is I would get photons coming over here, get absorbed, electrons scattered, re-radiate in a different direction. So I would get light that's scattered about. Right? And so if I look at it from different points, so it scatters about this way, this way, this way. So if I look at it from this direction, I would see the light over there being completely unpolarized. Basically, whatever didn't hit the dust particles is going through. The light that's coming about in this direction, that's 90 degrees perpendicular to the incident. This is going to be, if I look at it from this direction, I can see that this is 100% polarized. If I look at it anywhere in the middle, and I can have a different angles here, if I look at the light from here, it'd be partially polarized. And also, what's that? Mm-hmm. Yeah, this is. Oh, you mean this one? That's parallel to the wave incidence. Is that what you're talking about? You're right. I mean, it wouldn't. The probability of the light scattering off a dust particle going straight up, that is, the probability for that is 0. But I mean, this could be the light that didn't scatter off this dust cloud, and it's just going through. Oh, sweet, thank you. No, so I have a single photon over here. It's along in this plane here. So it's going about in that. I mean, but the acceleration for this would be something like that for the particular one. So you wouldn't really see any acceleration in. Right. So you wouldn't see any. In principle, none of the light should get scattered off over there. But whatever light you see over there, that's going to be unpolarized. So basically, that's light that didn't scatter off the dust. Now, I sent them an email, and they got me the polarizers I was talking about. So let's look at that real quick. All right. So these two are linearly polarized filters. Basically, pieces of film. They have gratings in them that cause them to polarize. So if I put one of those filters on there, you can immediately see that the light has the intensity has gone down. Before we do, let me write you guys a message. There. So I put this on there, I wouldn't see anything. Put this on here, you can see the intensity, and if I put it partially up, I can still see that the intensity is less compared to the original. But as I turn this, gone. So you can see a little bit gone completely. And same with the other way. Completely gone. No, these two are both. So basically, once it comes out of this filter, it's 100% polarized. So right now it's unpolarized light. I put a polarizer here. It's polarized. So this light is 100% polarized. But all the light, so let's assume, I don't know exactly what direction it's polarized in, but let's assume that it's vertically polarized here. Right? So all the light is vertically polarized. Now if I place this, the other second polarizing filter along the same plane, right, so if it's along the same plane, in principle it's supposed to not even make it darker. So all the, so once, right now you have unpolarized light. Once I put it over here, this polarizing filter, let's say it's about this direction, right? So the light is polarized, which means that all the photons they're all in the same direction. Something like that, yeah. Something like that, yeah. So when I put this on there, assuming that it's in the same direction, everything is kosher, then all this is in the same direction of polarization as the other one. So the light's already polarized in that direction. So all the light would go through the other polarizer, no problem. The intensity wouldn't go down. So none of the light would get blocked off. But as I change this angle, so this vertical one, so not the vertical one can't go through. So I have to break it up into components, and only part of that, so the cosine of the angle, can pass through this to a point where when it's completely perpendicular. If this is going this way and the polarizer is in this direction now, the second one, right? So it's basically these two are perpendicular, so none of these can pass through. So right now you have well, pretty much for all intents and purposes, no light coming out of there. Right?
So what happens if you had a third sheet and you had them first one like offset like 45 degrees,
Uh-huh.
and then the third sheet at 90 from the initial?
So what you'd get is, after the first sheet, I'd get something like this, right? Second sheet, if I put it at 45 degrees, the intensity would be lower, but I'd get something like this, right? And if I, so basically light now, all the light is in this plane, 45-degree plane. Now if I put another sheet that's 90 degrees to this, so it's the polarizing filter is horizontal here, let's say, then only the light that's horizontal will pass through. So only the horizontal component of this light will pass through. So the light won't be 100% blocked out, but you'll get a smaller element, but you'll get some fractional component of this that's in the horizontal direction.
So you'd actually get more through if you had
Different levels. Yeah.
in between two 90-degree polarizations.
Mhm.
That was that offset from both.
Yeah, in principle you would. So basically the idea here is that if the polarizer is perpendicular to the direction of the light coming in or going through the polarizer, if it's perpendicular, then it's going to block everything out. So because there is no there's no cosine component here, it's 0. So if I were to have this second filter on, and the third filter would be perpendicular to the second filter, then you wouldn't get any light. So because after the second filter, the direction of light is at some angle that you put it at. So if it's if I put my next filter along in this direction, then I wouldn't get anything. But otherwise, yeah, you would still get something until the point where the intensity is so low that you can't see anything, which can also happen. But I always thought it's pretty cool. You can also do this with your faces. Now you can see me now, and you can't now. And I can't see the light over here either. So, ow. So that's also the case. Okay, polarizers are quite awesome. Did you guys know that pilots? So most of the aviator sunglasses, you can't really. I mean, the proper ones, you can't get polarized, because the LCD screens in airplanes are all. I mean, like I said, they're all polarized at a certain angle. So their concern was that if a pilot was wearing polarized sunglasses, then if he was looking at it at a certain angle, he wouldn't be able to see his instrumentation. So most of the aviator glasses, the good ones at least, they're not polarized for that reason. So yeah, that's the fun fact of the day. We've got some time. All right, so where did we leave off? All right, so we have light coming in, hits the dust, scatters. Ones that scatter 90 degrees, 100% polarized. The ones that don't scatter go straight up. They're not polarized. The ones at some angle, they're partially polarized. And I'm missing a marker, but oh well. So, like I said, the particles you need are approximately about 1/10 of a micron to scatter. And the probability of blue light scattering is much higher than the probability of red light scattering. So blue light scattered, the probability of it scattering is far higher than red light. So shorter the wavelength, the higher the probability of scattering. So blue light has about 10 times the scattering probability of red light. So it's 10 times likelier that it will scatter than red light. And this is where the secret lies for our blue skies. I'm sure most of you when you were kids asked your parents why the sky is blue. Right? I did, and I got some answer I don't remember, but I know it's completely wrong. But now you guys know definitively that it's blue because of scattering that goes on. So our atmosphere has dust particles. Sun comes in, hits it, the light scatters, blue light scatters more than red, so you see blue skies. For those of you smokers in this room, not that I condone that, but or not that it matters if I condone it or not, but if you at some point were near a source of light smoking, you can see that the smoke coming out of the cigarette, it has a blue tinge to it. It has a blue hue to it. But at the same time, if you inhale it and then you blow it out towards some light, you'll see that it's pretty much white. Because when you inhale it, you pick up the water molecules, the moisture from your lungs, and those are considerably bigger than the dust particles. So you'd get some white hue. So basically, there's no particular preference of the color scattering to get just white light. But the dust particles from the cigarette, when you're smoking, if you're standing by light and you have light shining on it, you can see a blue tinge. It's actually quite noticeable. So that's another reason clouds are white. So light hits it from the sun, it scatters off, but it's white because there's a lot of moisture there. So you can see white light. So there's no particular preference for the frequency of scattering. So you'd see all the frequencies pretty much scatter the same probability. So if I'm standing here and I have the sun up there, it's now midday, and I have light coming in. All right. So light's coming in, hits the dust particles, and it would scatter. Once it scatters off, you can see, like I said, blue light is 10 times more likely to scatter as red, so you'd see the sky as being blue. And it scatters off air molecules themselves and also fine dust particles. And there's also quite a lot of thermal fluctuations in the atmosphere that's going on all the time that changes the density of air, and these are also sufficient to act as scatterers when the density changes in the air. So I have light coming in from different directions, and when I look at it from any one of these, right, I can see that this direction, blue is 10 times likely to scatter. So you'll see sky light being blue when you look at the high sky. And if you have your polarized sunglasses and you look towards the sky, if you change the angle that you're looking at, you can see the intensity also go down, and that'll also that's an indicator that it's linearly polarized. Right, so, but of course, you can't completely block it out because it's not. I mean, except there will be a point. So along the sun, there's going to be like one certain plane that is perfectly 100% polarized, or close to like 90% polarized. And if you're wearing your polarized sunglasses and you go out and you tilt your head to a certain angle, in principle, you could block out most of the light. But the light that we can normally see, that's not really 100% polarized, but it is polarized enough where you can notice the effects. But the sky actually is quite polarized. And so this, what I'm showing you here, that's during midday, more or less, when the sun is above you, like right now. And it's ridiculously hot. Well, heat doesn't really have to do anything with it. It's just, but so let's look at the other situation. Well, same thing. But when the sun is along the horizon, when it's about sunrise or sunset, right? So it's depending on what sunset or sunrise, it would be coming in from the horizontal plane, right? So you have light coming in towards you, something like this. Now at this point, the light also would still scatter. Right? You'd see light scatter, some blue would scatter away, you have some clouds here. But when it's along the horizon, that light has to travel a lot more distance than it would if it were right above you. So because it has to travel a lot more distance, it still scatters, and you're right. I mean, light, the ability for light to scatter blue light is about 10 times higher. So, but by the time this light reaches you, all the blue light has been scattered away. So what you effectively see, as I'm sure most of you have enjoyed some perfect sunrises and sunsets, you'd see the clouds more or less being red, and you'd see the sky also having red color to it. And that's because all the blue in the light has been scattered away, and all that's left when the light gets to you is red. And depending on the time of the day or where the sun is, more of the light is more of the blue is scattered away, and if it's as it gets higher, the less of the blue scatters away, so you can actually see the blue once it's above you. So this is quite an interesting thing, and like I said, the scattering is this. Again, in astronomy, they use a lot of these techniques to see to make out the composition of various stars and so on. One of the examples is called the Seven Sisters, and they're hot stars, and no pun intended. So what I have here is right. So this is an image of the seven sisters stars. So you can see, I mean, of course, there are more than 7 stars. There are hundreds of stars in that particular composition, but you have fine dust around them. And because of that, you can see the blue light scatter over there, and you can see the blue hinge there. And I'm sure most of you have seen the pictures of the astronauts walking on the moon, right? Neil Armstrong and all of them. And there's no air there, but when you see the sun behind them and they're walking, they can kick up dust, and that dust also is quite fine. So when that dust is up in not the air, but up around them, you can see the light scatter away from them. You can see the blue light scatter, and you can see a blue tinge around them, and that's also because of scattering. Here's a animation I found on the sky. So you have the sun here, and I can see the light polarized in a certain direction above there, and when it's along the horizon, you can see it scattered or polarized mostly on the vertical. This is showing you that basically it hits the light, and it scatters perpendicular to the incident beam. That's always the case. I mean, the direction in which it goes is different, but it scatters about there. But yeah, all right. So now you guys know why the skies are blue. There was actually quite a good demonstration. If you guys have an opportunity in the future to go to the physics festival, there's a demo, and it's basically a big gigantic tube filled with water, and they have some contaminant in there that acts like dust. It's a really fine particle that's contaminated in there, and you shine light at basically a big old halogen bulb on one end. You can see it really blue in the beginning, and as it gets towards the end, you'll see it being red. And that's just from light scattering off in the beginning. And if you take a red laser and shine it through, it'll pretty much almost go through no problem. But if I take a green laser or a blue laser and shine it through, in the beginning part, it's going to scatter most of it away, and none of it will actually end up in the end. So that's another cool thing you guys can see with that. I try to get the demo here. I'll see if I can get it on Friday, but yeah. Right? I'll see you guys on Friday. Hopefully I'll have your exams by then.